Today's session is on the continuation of the previous lecture, Gauss Law and applications. Gauss Law. So we have already discussed that Gauss Law is used to determine the electric field intensity or flux density over any surface. So let us see how you can determine the amount of charge within a closed surface simply by examining the electric field on the surface. What is meant by electric flux? How can you calculate it? All these things we are going to discuss today. Consider a charge inside a box can be probed with a test charge Q0 to measure the electric field outside the box. So this picture clearly depicts the box which contains a charge Q. So whenever there is a charge enclosed in a particular place, that can be probed by another test charge, so as to measure the field which is exerting outside the box. And volume, that is a volume V is and it has a flow rate of dV by dt. If we consider a wire rectangle which is having the dimension A, when the fluid is passing through it is perpendicular to the velocity of the vector, and which makes an angle VA cos phi when the rectangle is tilted at an angle phi. So next, if we replace the fluid velocity and flow vector with the electric field vector E, and finally the outcome will be the electric flux psi E. So this is the way we can identify the volume flow rate through a wire rectangle. A flat surface in a uniform electric field. See, a flat surface like a panel or something like a rectangular box or a rectangular sheet. The electric flux through the surface is equal to the field into the area of the entire surface. So when the area vector makes an angle phi with the vector E, the area projected onto the plane will be oriented perpendicular to the flow. Therefore, the area perpendicular is equal to A cos into that area. If the flux is has to be identified when the angle which forms is equal to 90 degree, then the flux will be 0. Why? Because the rectangle lies in a plane parallel to the flow and no fluid flows through the rectangle. Electric flux through a sphere centered on a point charge Q. So whenever we intend to identify the flux due to the point charge Q, immediately an imaginary surface or a Gaussian surface has to be identified for the suitable situation. So since this is a point charge Q, a Gaussian surface will be a spherical surface. So the phi E or the flux induced is calculated as phi E is equal to integral E dot dA, which is equal to E dA cos phi, and E dA, E is a constant value, integrating over the differential area dA is gives 4 pi r square. So the next step is 1 by 4 pi epsilon naught q r square into 4 pi r square, both gets cancelled. The answer is q by epsilon naught. Therefore, the electric flux phi E is equal to q by epsilon naught. Therefore, the Gauss law can be defined as phi E is equal to E dot dA, which is equal to q enclosed by epsilon naught. Flux phi E from a point charge Q. So consider this diagram. The projection of an element of area dA of a sphere of radius r is up into a concentric sphere of radius 2r. The projection multiplies each linear dimension by 2. So the area element of the larger sphere is 4 times into that. The number of flux lines pass through each area element. flux through an irregular surface. So how to determine the flux through an irregular surface? So the projection of an element of area dA of a sphere of radius r up to onto a concentric sphere of radius 2r. The projection of the area element dA onto the spherical surface is dA cos phi. So if the surface is irregular, we have to identify a suitable Gaussian surface based on the nature of the charge. Spherical Gaussian surfaces. See here, the two surfaces are shown here. The Gaussian surface around a positive charge that exerts outward flux. The positive charge is at the center. That charge exerts outward flux, and the Gaussian surface is of a spherical in nature with radius r. Whereas the picture B depicts the Gaussian surface around a negative charge. That in that situation, always the flux are pointed inwards. The Gaussian surface is shrinked. So these are the two Gaussian surfaces for positive and negative charges respectively. Hope you understood the necessity of Gaussian charge and what type of Gaussian surface can be applied to identify the flux lines. Hope you understood the session. Thank you for listening. Thank you.